All right, for part one of this, we're going to do our free body diagram for mass A on the left-hand side, mass B on the right-hand side. We can see for mass A, it's going to be falling just purely translationally, straight down. The net force is down. The force that's pulling it down is mass times gravity, it's weight. And the force pulling up against that is the tension on the string. On the right-hand side, we have, much in the fashion of a yo-yo, the string is attached on the radius, on the circumference of our disc. So there's a tension going up from the side. And this is not going to be moving purely translationally. It is going to be falling straight down, but it's also going to be spinning. So there's some rotational as well as translational. The net force on mass B is also going down. The force pulling it down is gravity acting on mass B, its weight. And then again, there's the force of tension pulling up on the line here. So we write down our net force equations for both of our masses in red for mass A and in blue for mass B. From there, we're going to solve for both of these in terms of T, the tension. So the net force can go away. We'll just move it over, and tension is going to be its weight minus ma. Now, since our pulley has no mass, that tells us that the tension on the left side, the tension on the right side, those are going to be equal to each other. And it tells us in the problem that both of our disks have the same mass, so we can simplify our equations. And we can set our equations equal to each other. From there, mass will drop out since all the masses are the same. And we can move gravity to the same side. That's going to give us gravity minus gravity is going to give us 0. And we'll end up with just A is equal to B. So that means that both sides are going to have the same downward acceleration. And that means they both should hit the exact same time. So for part 2, here's where things get fun. Now we're going to try to figure out, well, what is that time? And the trick here is we have to understand that B, its angular acceleration, has to account for both its downward acceleration, but it also has to feed out, it has to turn fast enough to feed out enough line for the other puck to accelerate downward at A as well. So the acceleration of B has to be twice the acceleration. And so alpha is going to be 2A divided by R. All right, we also remember that torque, because we're going to need that for our equation, torque is the product of the radius and the force. In this case, the force that's causing it to turn is the tension. And we can pull the equation from tension from what we got before on the right-hand side. And our equation will give us R multiplied by mg minus ma. So we're going to feed both of those equations into the torque equation, pulled directly from y'all's equation sheet. So torque equals I alpha. We know what torque is. We know what alpha is. Now we're just going to substitute in. And here's where the algebraic nightmare begins. All right, so we substitute in, and now we have to clean up this mess. So first of all, let's move R over to the right-hand side. So that way we can get the parentheses in green and remove that. So I already have an R on the right-hand side, so he's going to go hang out with his friend, and I'm going to get R times R on the bottom. Now, while I'm here, I'm going to go ahead and pull mass out. So that just leaves me with G minus A. And I could also move mass over. It can go hang out with the R. So that will give me g minus a is equal to I 2a over m times r squared. Now we can move a to the right side. A is going to become positive and it's going to add on. And then we're just going to clean up things a little bit better. So I'm trying to pull a out of the right side. And when we factor a out, if it's just a by itself, then I have to leave behind a 1. We can't just make it disappear. So it's like I'm dividing a out. So a divided by a leaves me with 1. When I divide a out of the right group, that's going to leave me with 2i over mr squared. And normally, depending on the shape of our object, if it was a uniform object, we could substitute in the equation for I here, and we could clean up mr squared. But they tell us specifically in this problem that I is not equal to 1/2 mr squared. So it's not going to simplify just yet. We'll end up having to plug in a number for that. But let's keep trying to manipulate and move this around to solve for a. At this point, it's pretty easy to get a by itself. We can just divide the parentheses to the left-hand side, and it gives us this huge mess. And so this is the goal of everything that we've done so far, to get acceleration. That's not our final answer. So once you solve for acceleration, that is going to allow us to find time. And to do that, we're going to use our good old equation from kinematics. So the distance is equal to the original velocity times time plus half the acceleration times time squared. Now we know the distance that this falls is its height. We know it starts from rest, so initial velocity is 0, and so we can simplify this equation and cut it down to just height is 1/2 at squared. So the final trick, solving for time, and that's not so bad. So our final time is just the square root of 2 times height divided by the acceleration. The acceleration you solved from the previous equation. I don't recommend trying to merge those two. You can, but it won't be pretty. All right, that's it.